Hello, everyone. This is Brian Wolford. This is our 2-minute warning. Hello, everyone. This is Brian Wolford. A 1-minute warning before we start. Okay, everyone. The time is 10 o'clock. We're going to begin our presentation. I want to say thank you to everybody for giving your time and attention to attend the Sensible Fan Power Terminal and Chilled Beams presentation. As I like to coin it, a perfect marriage. Today, presenting is Mark Mann. He's got a BSME from the University of Manitoba, and he's the Applications Manager for Terminal Units at Price Industries. A couple housekeeping items. We'll all be on mute for the presentation. I ask that you type in your questions in the chat bar located on the lower right-hand side, and I'll be the moderator at the end of the presentation, and we'll go through your questions. The intent of the presentation is to introduce the idea. We have a much more in-depth version where we can do about a 45-minute presentation that goes more into details on it, and you can do that on a case-by-case basis for your firms if you like these ideas that we're introducing. With that said, I'm going to turn it over to Mark Mann. Thank you.
Great. Thank you, Brian. And thank you, everyone, for attending. And yeah, I think that's a great kind of summary and background. You know, we're gonna look at this idea of pairing together fan-powered chill water terminals and chilled beam systems. They're kind of a perfect matrimony. Brian and his genius marketing and his team with the wedding cake, I'm sure, caught a lot of eyes. I thought it was hilarious. But to paint that picture a little bit, you know, in more depth, we can do that as Brian suggested. At Price Industries, we do have a full chilled beams division and team, and we'd be happy to loop them in as well and provide, you know, a more in-depth look at this kind of system and running it with fan-powered chilled water terminals as well. So that's something we kind of do as a tag team effort at times. I guess to start off, and you know, I don't think this is necessarily something an idea that needs to be sold in Washington State, but it is still important to review. And it's just the idea of why do we utilize dedicated outdoor air systems. So the reality of our dedicated outdoor air system, I think, is best summarized by kind of the airside consideration in comparison to traditional VAV. When we look at a traditional VAV system, that airflow, that airside portion of the system is responsible for all sensible cooling, latent cooling, and ventilation. When we look at a dedicated outdoor air system, which is essentially operating on the core belief that we should only provide the minimum ventilation required for or the minimum amount of outdoor air required for ventilation and for latent loads, we're looking then at a partial sensible latent solution or partial sensible airside solution. So that outdoor air is only providing part of the sensible load. It's taking care of that latent load and ventilation airflow as well. And this results in some significant benefits. So we have benefits in energy savings. We generally see about 30% potential energy savings when looking at kind of open office environments with dedicated outdoor air systems. And we're also seeing significantly reduced ductwork. So that reduced ductwork comes into play because the volumetric heat capacity of water is so much greater than air. At standard conditions at sea level, we're looking at a volumetric heat capacity for water that's 3,500 times greater than that of air. So extremely, extremely significant. That's equivalent to an 18 by 18 inch traditional VAV air duct being broken down and compared to a 7-inch dedicated outdoor air system air duct and a 1/2-inch diameter water pipe. Those are equivalent from an energy transportation perspective kind of throughout the system. So because of this, we're getting reduced duct size, reduced mechanical equipment sizing. We're also seeing better comfort in the zone because of the decoupling between humidity and temperature responsibilities. So another thing that's worth noting here, when we look at this airside consideration, I just want to paint the picture of that energy efficiency. Oops. Sorry, everyone. An update that's forced in an hour, so we're fine. My apologies there, but thankfully that wasn't forced right now. That would have been good to have a little bit of a heads up on. Thankfully, we will not be interrupted. When we're looking at the airside considerations for this equipment, I just want to paint it a little bit more. This is a little bit of a case study that actually our beam team put together, looking at an open office environment providing 370 MBH of total sensible cooling with 55°F entering air and 57°F entering water. When we look at the power consumption of our fan and our pump in comparison to the power consumption just of our fan and a VAV system, we're generally seeing that 30% mark, but it can go up. In this case here, this was an office example that we were seeing 44% less peak load brake horsepower. So significant energy savings just because it's so much easier to move fluid rather than it is to move airflow through ductwork. So I just want to go through a brief kind of review of chilled beams and fan-powered chilled water terminals, and then we'll look at kind of utilizing those two systems together. So we're first looking at chilled beams here, and the big thing that I kind of want to, I guess, lay out is the general system design, because we're going to see kind of a motif as we move through, you know, looking at this system, looking at fan-powered chilled water terminals, and looking at the two together. So generally, we're seeing kind of that elevated chilled water for a sensible only solution. So we're seeing that 56 to 57 degree elevated chilled water temperature, allowing us to provide that sensible cooling throughout our system. We're looking at if we have some reheat, 100 to 140°F, and a typical 55-degree primary air that's often dried out a little bit additionally for providing that latent load to the space. As a general rule of thumb, we're seeing about 1 MBH or 1,000 BTUs of space sensible cooling per linear feet of active chilled beam. When we compare this kind of a system to a traditional VAV system, we're seeing substantial fan horsepower reduction. We're seeing a quarter of the total primary air supplied just because of that dedicated outdoor air system methodology. And then we're seeing that 30 to 40% more efficient kind of total system in comparison to traditional VAV. The other excellent thing that I think in particular, which we'll touch on more with chilled beams, is they are a very, very quiet system. We're generally seeing a system design of NC 30 or lower with this kind of a space. So what is a chilled beam? Well, hopefully we're mostly familiar, but as a quick review, a chilled beam is a sensible only device. So it's not providing any latent cooling. The latent cooling is coming from the air handler and it is supplied through an active chilled beam, for instance, but the intent of the chilled beam is it's a sensible only device that uses chilled or heated water supplied above the room dew point to cool or heat the space in which it's installed. So that primary air is being used to treat the latent load, and the chilled beam is being used to treat that space sensible load. There's really three types of chilled beams. The one that I see most commonly utilized and the one that is kind of intended for this discussion and application is really that overhead active chilled beam. It would be the most popular one, although we do see it in the floor mounted configurations, which we can see in the center of the screen. So the same kind of components, just reconfigured so that they're kind of in more of a wall mounted fan coil style configuration. And then on the right hand side, we see that passive chilled beam, which is having no airflow supplied directly to it. It's just entraining and mixing air in the space without the utilization of any primary. So when we look at how a chilled beam works, I just want to show this on screen here to review. We have that primary air being supplied into the chilled beam, and that primary air is accelerated through these high velocity nozzles. So we can see that on screen here. I'm going to click pause. That airflow goes into this kind of back plenum. It's supplied at a high velocity through the nozzles and thrown to the space. And because of that high velocity air, we're actually going to be entraining and inducing additional airflow through the face of the coil, which we're going to be able to cool or heat to our requirements, and it's being supplied once again to the space. So with this effect of air induction, we're generally seeing a much higher magnitude of air delivered than air supplied to the equipment. So we're usually seeing somewhere between, definitely in the realm of 2 to 4 and sometimes even more air discharged than air supplied, primary air that is. So now I just want to take a quick look at the basics of just our fan powered chilled water terminals, which is in many ways more my bread and butter. It's the product that I work with on a daily basis and the one that I tend to have the highest interest in. And when we look at system design considerations, really the nature of the beast here is that it's chilled beam performance with a fan powered terminal unit system layout. So we're looking at some kind of differences as far as how densely the equipment is supplied. So when I'm saying densely supplied, I'm talking about that energy density available at the equipment. For our fan powered chilled water terminals, we're seeing up to 36 MBH of space sensible cooling as a maximum for fan powered chilled water terminal. We're seeing the same primary air volume as chilled beams, so 1/4 of traditional VAV systems on average. We're seeing the same kind of water temperatures, so that 100 to 140 degree heating water temperature is very typical. That elevated sensible only chilled water temperature of 56 or 57. And we're seeing a primary air condition, once again, usually centered around that 55 degree primary supply, although we do see for kind of more higher humidity applications, that's driven down pretty commonly in our system as well, where we can get as low as 47 to provide a greater latent supply to the space. So when I say, really it is a chilled beam performance type unit in a fan powered series layout, it is true. And we kind of can see this on screen broken out a little bit more clearly. So we do have that primary air inlet, that primary air valve, which is maintaining the flow of ventilation air and meeting our latent load within the zone. We have that sensible cooling coil, which for all intents and purposes is kind of a chilled beam strapped to the side of our unit, which is handling the space sensible cooling load. And then we have that ECM fan, so that electronically commutated motor, which is very high efficiency, can provide quite a bit of airflow below the Washington State Energy Code 0.12 watts per CFM requirement. And it's also accounting for the downstream pressure requirements of the ductwork, the air pressure drop of the coil, perhaps the air pressure drop of an acoustical silencer or something of that nature as well. And what we're really looking at here, for those of you who are not familiar with series fan powered terminal units, is we're going to have an offset of air volume between the fan and between the primary air inlet. And because that fan is kind of discharging air downstream and inducing air from the equipment casing, from the inlet, and from, I guess, the plenum through the coil, the offset between fan and primary is going to be the volume of air we see drawn through the coil and cooled down by our elevated chilled water temperature. So So the other reason why this equipment is kind of become more popular in really the last year, let's say, is because there's recently been some significant industry improvements. And those are based in the fact that this equipment has been modified and updated for the wider market with a standard height casing. So a standard height casing being centered around 18.5 inches of height, but spanning from 15 to 20 and 1/8 in the case of the price terminal unit. The low profile unit existed previously and in the past. It gained a lot of traction and popularity in the Washington, D.C. region originally. They're a low profile market specifically because everything on, kind of the main Washington, D.C. epicenter there, nothing can be built higher than the Washington Monument, which creates some really, I guess, creative construction constraints where they're trying to squeeze in an extra floor and decreasing plenums. So when we see that, the low profile unit has been kind of the dominant terminal system in that market for about a decade, with the standard height version only really taking the market by storm now, which is why you might be seeing this equipment more and more as the months go by here. There's lots of benefits of using this kind of configuration in a dedicated outdoor air system. One would be that higher humidity applications are possible, and that's really due to that variable primary air inlet. So the fact that primary air inlet can measure and monitor airflow in real time and provide a significant amount of turn down is going to allow for kind of those blasts of higher volume dry outdoor air in some instances to condition higher humidity zones. Not something that's as critical for you guys in Seattle, but as we see this move its way definitely into the southeast will be a point of interest. So that crossflow sensor and damper also enables the monitoring and control of fresh air for demand control ventilation type systems. So providing only the amount of outdoor air that the system needs based off of zone measurements, whether it's occupant counting or whether it is carbon dioxide monitoring. The fact that we have this local fan is super excellent because it allows for morning warm up and night setback. So if we have an unoccupied mode through the night, we can actually turn our rooftop unit off, which is going to allow for significant energy savings, and we can still heat up the space and get it ready for occupation without having to turn on that rooftop unit. The provision of the fan reduces zone stratification and improves indoor air quality. So we can provide a higher volume of air than maybe we could with a chilled beam system, just with that fan still operating below 0.12 watts per CFM in deadband, which is going to allow for significant mixing within the zone, less stratification, and also as it continues to induce air in and mix it back to the breathing zone, any ventilation air that hasn't been utilized by the occupants can move back into the breathing zone, which is a benefit. That fan motor is going to allow for diverse outlet options just because it provides a lot of downstream static pressure flexibility. So long duct runs, multiple air outlets, maybe even mounting the unit overhead outside the occupied space. And then obviously that VAV primary and fan sequencing really allows for ideal operation within variable occupancy zones. So if we have significant swings, which is going to result in loads that change, our fan turn down can be up to as high as a 24-to-1 turn down. Obviously a VAV style primary air inlet has significant turn down capabilities as well. So we can only provide the conditioning that the zone specifically needs. And as far as how these are mounted, even in a dedicated outdoor air system style of building, it's going to look like any kind of typical VAV, typical GRD system, which provides a lot of architectural flexibility. So the next thing I want to look at, especially when we're considering kind of the combination of this equipment, is the ability to manage reheat options. I know chilled beams can provide reheat with kind of an interlaced coil, one kind of face coil with reheat circuits running through it. But I think the other benefit of doing a hybrid style of system is all of the reheat options that are available on these fan-powered chilled water terminals. So whether you want hot water heat or electric heat, there's different options at play. Electric heat can be offered on the discharge in either staged or modulating styles of reheat. We can see a typical discharge hot water coil, and then more importantly, especially for your market, I think that return reheat coil provides some significant benefits. And all of this is really important when we look at kind of hybrid system design, because I would tend to suggest that, you know, this kind of equipment is really best serving exterior zones with high heating loads or maybe variable loads, high cooling loads in the summer as well. So when we're considering these different reheat options on our fan-powered units, I think the biggest thing for the Seattle market, which tends to be, in my experience, a hydronic reheat market on this kind of equipment, and it also tends to be a very, very low heating entering water temperature market, we would really want to evaluate, you know, is the return coil optimal for us with our low entering water temperatures, which I would tend to say it is. So I've had projects as low as 100 degrees for reheat, which is very, very low and tends to be a bit of a design hurdle to get the heating capacity required. But with that large return coil, even with a 1 or a 2 row option, we're going to see the ability to provide a significant amount of heating capacity for those exterior zones within the design. Another thing that is noteworthy as well, and is especially important for you guys with that deadband requirement of 0.12 watts per CFM, is if we load up a piece of equipment with more air pressure drop, that's going to start to also drive up that watts per CFM operation, because a motor runs with higher watts as there's more external static pressure. So providing more of a low air pressure drop solution, such as a return reheat coil or an electric reheat option that has really negligible pressure drop, could be what's required in order to meet high CFM intended deadband operation, just because of that watts per CFM requirement. So next we're going to look at acoustics here briefly, which I think is a great opportunity for chilled beams in particular to kind of shine in this hybrid application. But first I just want to glance quickly at this fan-powered terminal unit again. And the thing that's really noteworthy here is the fact that there's two different sound sources. So we have that primary air damper and that motor blower assembly, both which are generating noise. But most critically, we have this large coil on the side of the equipment, which is essentially just operating as, you know, a hole for sound to travel through. Sorry, skipped over that a little bit briefly. So it's really operating as a hole for sound to travel through, which is a design constraint. I don't want to scare anyone away from using this type of a system, even in kind of sound critical applications. Recently, me and Brian have worked on a project where we're up to 1600 CFM in an open ceiling, still providing an NC35, which is very acoustically comfortable, especially for an office. But that project and many projects would require the utilization of an RSLR, or our return silencer, which is going to essentially stop sound from breaking out through that coil. And that's the sound that's generated both by the motor and the primary air inlet there. So an option like this is something that many manufacturers offer, but not all manufacturers. And when we consider open ceilings, cloud ceilings, all of these things that are becoming more and more common architecturally, providing a acoustically comfortable solution may require an option or accessory such as this, which can come in a 1 foot, 2 foot, or 3 foot option. And the 1 foot is what we see primarily being required. So the other portion of this holy matrimony, flying back to chilled beams here, you know, I think chilled beams, especially in a hybrid kind of solution, can really provide some significant value acoustically. Typically, we're seeing room acoustics of NC30 or less in chill beam type applications. And I show this one example of CHOP, an office in Philadelphia in particular, because this project, you can see the active chilled beams in the system. This is a price chilled beam project that actually ended up being too quiet for the office. So the chill beams were utilized, side by side. Employees were finding that there was really no white noise to kind of wash out each other's phone calls or discussions. So they actually put white noise generators in the ceiling on this project. Now that ended up being a design constraint that was kind of interesting, but I would argue, it's not the chilled beams that fell flat at all. That's really it's pure gold for an acoustician to be able to play with something that's that quiet. And with that in mind, I do think that, especially in a hybrid type open office application, being able to provide chilled beams in acoustically critical spaces can be a really nice combo. So this kind of leads us to this idea of hybrid design in particular. And we can see the schematic here with both those beams and the fan-powered terminal units kind of together in the configuration that I maybe think would be optimal, where we tend to have the larger turn down, more easy to integrate reheat fan-powered terminal units on the exterior zones, and then potentially some beams on interior zones. So we're seeing the same fan horsepower reduction on the rooftop unit. We're seeing fan horsepower reduction even with the inclusion of, all of the zone fans. We're still seeing far less energy consumption just because the volume of air being moved is less for a shorter distance. We're still seeing that quarter of primary air compared to all air systems, and we're still seeing that huge increase in efficiency. The benefits still exist as well. So we see this system being, architecturally flexible. We can use beams as an architectural feature. We can use fan-powered boxes to kind of hide our HVAC equipment and provide more architectural flexibility. These can work with exposed ceilings because of being able to utilize beams and being able to utilize silencer options for quiet fan-powered assemblies. So we're really just seeing a system that tends to slot together kind of perfectly. And I kind of want to close this off with a bit of an example, and I want to go through the idea of, where would we place this equipment within zones? And so what I want to look at is this floor plan here and consider, zone to zone, which technology do we implement? And what do we consider? Well, of course, we consider those acoustics, with chilled beams potentially being a bit more quiet, or at least definitely more acoustically flexible. Architecture is huge, so maybe we want a chilled beam style of ceiling, and that pleases the architect's eye, it pleases the building owner's eye. But maybe we also want fan-powered terminal units because they're more architecturally flexible. We have to consider zone loads. Are we in an internal or an external zone? What's the heating and cooling load? What's our occupancy, and is it variable? And then generally, how big is the zone as well? So in the chat here, I'd be interested to see your thoughts. We'll start with external zones here, because external zones can have higher heating and cooling loads. In this case, the zones below also would have variable occupancy and less stringent acoustical requirements, as they're kind of open office spaces. So in the chat, put FP for fan powered or put CB for chilled beam. What do you think would be utilized in this zone? Once again, FP for fan powered or CB for a chilled beam. So it's an interesting question. The reality is, I would say both are a great option. I would tend to lean more towards utilizing fan-powered units on these exterior zones, but I think that both can work. Now let's consider internal zones. So internal zones can have smaller cooling loads, considerably smaller heating loads. In this case, the zones below are also grouped together. They're smaller and they tend to be quieter because they're kind of office, or they're kind of meeting rooms or phone rooms, things of that nature. In this case, would we consider putting FP for fan powered or CB for chilled beam? Please just type in the chat FP for fan powered, or CB for chilled beam? Well, once again, I think the reality is you can use both. I would tend to lead towards, maybe for these smaller offices, maybe utilizing a small 2x2 active chilled beam, or for the larger meeting rooms, maybe a linear beam in there to provide our sensible cooling load. Being able to tie each of those into a thermostat without needing a fan powered box for each zone is going to allow control by the occupant within the zone, and is going to provide a really quiet acoustical solution for rooms that maybe need to have a little bit less generated noise. And then finally, corridors. Generally, these are the most acoustically flexible. However, they could also be kind of shoehorned into a specific design for architectural reasons, something of that nature. That's often what we see, in lobbies or kind of spaces that tend to have more movement. They often have a little bit more of an architectural design in offices. So what would we tend to see here? FP for fan powered, CB for chilled beam. Well, once again, not to spoil it, but the reality is you could use either. In this case, maybe a fan powered unit or a chilled beam, or maybe both could even be utilized. Now it's funny because I said fan powered boxes I would put externally, I'd put chilled beams internally. The reality is, in this project, they actually did the exact opposite, but that just goes to show how flexible this system can be being applied in a hybrid style. So with that in mind, any questions, please shout them out. Hopefully Brian can moderate for us here, but we do have contacts on screen here. You could also send myself an email. I could get you my contact information through Brian, and our Beam team's contact is there as well. If you're interested in having more of kind of thorough presentation on this topic, reach out to ACI, and we would love to get something prepared.
Thank you, Mark. So I've got some questions up here, and I also wanted to chime in a bit on the votes on the perimeter did come out as more fan powered, and then a little bit more towards chill beams on the interior is how the voting came in. First question we have is from Glenn. What's the common pressure drop through active chill beams, and how does that relate to the fan powered terminals? Mark, if you don't mind jumping back, I'll tackle that one a bit on there. I think that picture of the interior exterior zone will help out here. So on a chill beam, you'll have anywhere from about a 0.25 to about a 0.7 inch pressure drop. On the sensible fan powered terminal, it typically will see a 1/4 inch on there. Now, one thing I was going to point out, if we take Mark's advice of maybe we look at those sensible fan powered terminals in the perimeter in the kind of purplish periwinkle blue color there, it likes to see that lower internal pressure drop, versus if we push the chill beams on the interior, that's essentially pressure drop that we have to get to the exterior. So it's almost like free additional pressure drop on those chill beams. So that's kind of an interesting thought process of use the chill beams on the interior where they want to see a bit more higher pressure. And as we have losses through the ductwork getting to the sensible fan powered, so they like to see the lower because the fan picks up the remainder on it. So that's how I would address that one. Let me know if that answers the question, Glenn.
Brian, I have to say you're reading my mind on that as well. I think using, for those longer duct runs, when we're looking from the longest distance from rooftop to, exterior wall, being able to utilize a fan powered box in that case to kind of lean out our rooftop fan as much as possible, and then further energize that for air delivery to the exterior zones is a great design element to improve on efficiency further.
Yeah, I like it, really maximizing the horsepower of the rooftop unit. The next question comes from Sergio. What's the difference between fan power terminal units and fan coil units, and its comparison versus a fan coil units? Do you want to take that one, Mark?
Sure. So I think, the main difference is where the water temperature is at. So if we look at a fan powered sensible terminal, it's going to be above the dew point of the plenum, resulting in sensible only cooling, while our fan coil unit is going to be really very strongly in the latent cooling zone with an elevated water, or sorry, a non-elevated chilled water, somewhere like 42 to 45 degree Fahrenheit. That's also going to require a full condensate management system. And generally, fan coils are going to run as a separate parallel system to our ventilation delivery. I think, both can be utilized great and can be a fantastic solution. If we're talking about a hybrid solution, the fan powered terminal is going to go much better with a chilled beam. And if we're talking about a dedicated outdoor air system type piece or design, we're going to see that better utilized as well. Really using fan coils in DOAS applications is most common when latent loads are higher. I would say it's more optimal to use the fan powered terminal unit when we have lower latent loads, which you guys tend to in Washington.
Mark, I appreciate that. Thank you. Okay, so it's 10:33. We're a bit over time here. I don't see any other questions coming through here, so I want to thank everybody again for attending. And Mark, thank you for the well done presentation. We will see you next time.
All right, thank you, everyone.